In Lecture 6, we finished our exploration of classical mechanics in its traditional Newtonian formulation, which sees classical mechanics as fundamentally a dynamical theory. Newton's laws tell us how to solve a particular initial value problem that I've termed Halley's second problem. Given known forces, or as we developed during lecture 6, lecture 5, I'm sorry, known force fields, we can figure out the trajectory of objects as a kind of initial value problem from ODEs. Now we're going to start developing the later Lagrangian formulation from the 18th century. But today, before we can do that, we need to develop some of the machinery that we'll be using. And to do that, we'll go from dealing with dynamical theories to dealing with a type of theory that you almost never see in physics before this course, optimization theories. Now, you may have encountered these somewhere else. Certainly, you should have encountered them in your first introductory calculus class, but they're not as common in physics, or they certainly weren't before the 18th century. Let's look at a basic optimization problem. The question is this: given a known function, f going from r to r, what is the minimum or maximum of f? Let's deal with the minimization problem now. Here we'll assume that f is twice differentiable so that all of our tools from calculus are available to us. The typical steps are this. First, we'll find all the places where the first derivative of this function is 0. I've graphed it up above, or just an example up above, and we find that for this example, the 3 places we see are here. So that's step 1. Check extremal points. Or maybe I should say stationary points. And that's just a synonym for f prime of x is equal to 0. Great. Okay, after we find stationary points, we need to determine which of these are minima at all. To be a minimum, we need to find that the second derivative of x is greater than 0. If it is 0, then we have a saddle point, and if it's less than 0, we have a local maximum. And I should say here, yes, local minima. All right, so in this case, we have local minima here and here, but this is a local max. Good. Okay, the last step is to find the global min. And so we just need to plug all of our local minima into the function to see which one is the smallest. In principle, at this point, we also need to plug in the 2 endpoints, but I'm dealing with a function depending on the entire, or whose domain is the entirety of R. So I don't have that problem here. Okay, you're again hopefully familiar with this kind of optimization problem already from calculus. In fact, it's one of the first things that you see in calculus that really proves how powerful it is. Now, calculus of variations is an attempt to extend this kind of optimization theory to functions from the real numbers to the real numbers, to functions from function spaces to the real numbers. So first, we're going to need to define a new kind of object. A functional is a, let me say, smooth, by which I mean infinitely differentiable. We could probably relax that somewhat, but smooth is the only case we'll care about here. Is a smooth function from a function space to R. Okay, let me give you an example. Well, suppose that I have a function. Oops, hang on. Suppose I look at functions from R to R. So we'll take functions from R to R. And for each one, we'll assign that function a value in R. And here's what I'll choose. I'm just going to take the maximum height. So the maximum height is a function from our function space. To the reals. But it's not a functional in the way that I'm talking about above because it's not smooth. Imagine a function which is somehow nearby to this function here, except that this bump gets raised up a little bit more. Well, if that happens, so if I raise this bump, and I'll sketch in that function as a dotted line, but change no other part of the function, then this point could become the new maximum height. And so a function which is somehow far away in the function space from our original function, which is somehow close in our function space to the original function, could have a different height that makes this map non-smooth. So when we think about functionals, which work nicely in our case, we're going to need to look a little bit further than functions which just take functions which just take a certain point of our given function here. In particular, a nice example is the integral itself. So here's a second example. So let's take functions from an interval, let's say a, b, which is a subset of R, actually not equal to R, we'll say it's a proper subset of R, and it takes those functions to R. And in fact, yes, it's just the integral. So here's A, here's B. I should be labeling my axes here. And we'll take functions like this, or like this, and we'll map each function to its integral. Now, I should probably say integrable functions. And typically in physics, I would even restrict my focus further to something like differentiable functions, or at least continuous functions or something like that. But in any case, it turns out that this kind of function from a function space to R works much more nicely than the kinds of functions that take a given function to a certain point, like its max height or something like that. All right, so we'll restrict our focus mostly to functionals of this form. Let's come up with a very general way that we could write functionals of this form. Now, perhaps it's an integral of a function itself. So I could write, in this case, the integral of f of x. So f goes to the integral of f of x dx from a to b. That's the function that I'm thinking of. But in fact, I could put other stuff in my integral as well. Integrals are very nice. They have all of the nice smoothness properties that we would care about in order to be able to work nicely with our functionals. So I could put f of x in here. I could also put any function, any composition of f of x with another function in here. So I could, for instance, take g of f of x for any function g, which still allows me to do the integral. I could also take functions of f prime of x, or even f double prime of x. It turns out that all such derivatives of f are also on the table. So here's a very general form. So I'll call my functional, should be giving it a name at this point. I'll call it L. Actually, maybe L is not good. I'll call it A for now. So A takes in F. A lot of the literature uses square brackets for functionals, so I'll do the same. And it is defined by the integral from A to B of some other function in here of F. And maybe at least in this line, I'll be clear that it's F evaluated at X, F prime evaluated at X, F double prime evaluated at X, and so on and so forth, and also possibly X itself, dx. This is a totally fine form for us to be able to do methods from calculus of variations. Okay, so I've only set up what kinds of functionals we can deal with. We have yet to figure out how we would approach the optimization problem for functionals of this kind. Now, this is not a task that is unique to physics. There are lots of reasons that we might want to be able to optimize various functionals. I'll give you a few examples a little bit later when we hop over to the computer. For now, let's just try to connect this to some sort of machinery. All right, that's where we go to starting to talk about the Euler-Lagrange equations. All right. To do that, what we're going to do is take A and stick in F, but also a small amount of another function. So I'm going to multiply this, I'm going to add epsilon phi, where F is, of course, a function. Phi is also an arbitrary function. And epsilon is just a positive real number. Oops, positive real. Now, where am I going with this? Well, if I'm at a minimum over here, and I add any other number to my input, then that result is going to be greater than the value of my function at the minimum itself. So we expect the exact same thing to happen over here. The value of A at any point near to this function f, or I should say any function near to this function f, if f is a minimum, should be greater than f. All right. So what we're going to do is take our integral now, again from a to b. And I'm doing this for one-dimensional functions. Let's keep that clear, at least for the time being. F of x, f prime of x, and let's stop it there. So let's do this only for the case where we have none of the higher order derivatives. Those turn out to be things that we can handle, but we have a much easier time if we only go up to the first derivative in the integrand. Okay, and I'll also include x in here, except I've forgotten to add my extra functions. Plus epsilon phi of x, f prime of x, plus epsilon phi prime of x, and then x dx. Good. Okay, so for every epsilon phi that I add, I hope that A will be bigger. But that also means that if I'm around a minimum, taking a derivative of this left-hand side with respect to epsilon should give me 0 if f is a minimum. And let's think about the same thing over here. If I look at this point, and again, this is my function f here, and let's call this point x naught. If I look at f of x naught plus epsilon delta x, well, certainly that point is going to be either on this side or this side. Let's say it's here, x naught plus epsilon delta x. And if I take the derivative of this as epsilon goes to 0, delta x, well, let me use the chain rule to figure out what that gives me. First, I'm just going to get f prime evaluated at the inside, x naught plus epsilon delta x. But then I'll also get delta x from the chain rule. But if I now set set epsilon equal to 0, then this gives me f prime at x naught times delta x. But by assumption, f prime of x naught is equal to 0 because, again, it's a minimum. So we're hoping the same thing is true over here. Let's take an epsilon derivative of both sides and see what happens. Okay, so d epsilon, again, we're going to set epsilon equal to 0 at the end here. A of f plus epsilon phi, evaluated at epsilon equals 0, is equal to what? All right, on the right-hand side, the d epsilon can go right through the integral. That's because the integral is over the variable x, and epsilon is a different variable. All right, so the d epsilon is going to hit this g, which remember is just a regular function of 3 different arguments. Only 2 of those arguments have an epsilon in them, so we'll only need to worry about those 2 when we take the chain rule. Let's hop to it. So we'll have an integral from a to b of, now we'll need to take a derivative of g with respect to its first argument. This can be somewhat confusing, but we denote that by dg df in most physics textbooks. Just remember that really what this means is just the partial derivative of g with respect to its first element. Then we evaluate that partial derivative at f of x, f prime of x, and x, where I've already set epsilon equal to 0 in my evaluation. Now remember, I also have a term from the chain rule. In particular, in this case, it's phi of x. Wonderful. All right. The second term is very similar. It's denoted dg df prime, which again can seem like a mysterious notation, but it just means the partial derivative of g, an ordinary function of 3 variables, with respect to its second argument. I evaluate that partial derivative at the exact same point, again setting epsilon equal to 0, and again I get another term from the chain rule. Okay, and that's all I get because this last argument does not depend on epsilon at all. Good. Now I have these 2 parts. And what I'm going to do is use integration by parts on the second term. That's because I have a phi prime here. So integration by parts seems like a smart choice. By the way, let's just point out what I'm doing here, just really quickly over the side here. I'm saying that for a minimum, for a function that minimizes this functional, this expression should be 0. That's going to be very important to keep track of going forward. Okay. Next, let's pull our equality over here just to give ourselves a little bit more space. We'll just rewrite the first term. And now we need to do our integration by parts. Let's really quickly break down what the different pieces that we're going to use are. So for our integration by parts, our u will be this part, and our dv will be this part. Good. okay? That implies that v is just phi of x. So the next thing that we have is plus partial g partial f prime, evaluated at f of x, f prime of x, and x times phi of x, and that whole quantity evaluated from a to b, minus another integral. Okay, now what I need to do is take an x derivative of u in order to get du. So this is going to be this integral, and inside we'll get d dx of partial g partial f prime of f of x, f prime of x, and x, and then a phi of x outside of that dx. Great. Now, even though we're choosing phi arbitrarily, there's one place that we are allowed to make a simplification here. The proof kind of goes a little bit beyond what I would like to do, but I'm allowed to choose phi specifically so that its endpoints, so that at the endpoints it vanishes. So I can, up here, note I can choose phi, so phi of A equals phi of B equals 0. And that's important because it means that this term just vanishes. Wonderful. If you go to a calculus of variations textbook, they'll do the proof that you're allowed to deal with only functions of this type. All right, but for us, now we have just a single integral, once I combine these two integrals together, that depends on phi of x as a sort of factor that they share in common. Okay, so let's actually pull that out front here. Phi of x times a big quantity, partial g partial f, evaluated at f of x, f prime of x, and x, minus d dx, partial g partial f prime, evaluated at f of x, f prime of x, and x. Close that one, and then close this one, dx. Good. Now the key is that because phi is arbitrary, there's no way that this quantity can always equal 0. So let's box that that's what we're trying to go for. There's no way that this quantity can always equal 0 for all phi of x unless the quantity in parentheses is 0. And this gives us the so-called Euler-Lagrange. I am still on the board. Okay, good. Equation. Which says that this quantity is exactly 0 for the solution, which is not necessarily minimal, but stationary, a stationary point of the action. So I'm going to erase the board and come back with the Euler-Lagrange equation and its statement written up. All right, we're back. So on the last board, we figured out this sort of correspondence between the way that we optimize real functions, in other words, find their global mins or maxes, and the way that we optimize functionals, a concept that we've just introduced. So recall I wrote those steps on the last board. First, we find stationary points. We check whether or not each one is a min, a max, or a saddle point, and then we can find the global minimum from the set of local mins, if we're indeed trying to find the minimum. Now, for functional optimization, what we've shown is how to do the first step. If we can find a function f for our sort of set of functionals that we like, which are describable as integrals, if we can find a function f satisfying the Euler-Lagrange equation, then we know that it is a stationary point of that functional. We often don't actually engage in the second two steps, although they are possible. We would need to define another second functional derivative to do this one. So let me just write that. Need to define a second derivative on the functional. And we can do that using this f plus epsilon phi strategy that we used for finding stationary points as well. But I'm not going to show you how to do it. And in fact, most physics textbooks will not take you through the way that this part works. For that, you would need to go to a mathematics calculus of variations textbook. Then, of course, if we did find all that were minima, we could do the exact same thing that we do for ordinary functions. We would just do the same thing and plug them back in to the functional. Good. So now our job is to find an f which satisfies this equation. And if we find such an f, we know that it will be a stationary point of our functional. Good. For our purposes, that will be enough. We'll always assume that we actually have an extremum in that case, and that it will be sort of obvious whether or not we have a minimum or a maximum. That will become obvious in the examples that we deal with a little bit later. But before we hop over to do those examples, I want to generalize this just a little bit. Now, before we move on to the computer, I want to generalize this formalism just a little bit. Instead of looking at functions f that go from the real numbers back to themselves, let's look at functions which are vector valued. So f is this, in this case, is going to take r to rn. It turns out we can deal with functions that take rn to r to rn, or rn to rm, but this is going to be the case that we need in this course most often. Okay, so I'm going to define that again on an interval a to b, and I'll still have a g in here, which needs to be output a real number if I want a to be real valued. However, in this case, it can depend on f, then f's derivatives. I'm going to make this integral, rather than being over x, I'll make it over t. So I'll use a dot here just to make clear what's going on there. And then t dt. So just to be clear about what's going on with g, g is an object. Again, because f is has codomain Rn, g is an object which has n plus 1, so 2n plus 1 arguments. Its arguments are f1, the first component of f, f2, f3, and so on up to fn, and then f1 dot, f2 dot, and so on and so forth. And I guess just to be clear for the time being, let me make sure that it's clear that these are evaluated at t. Now, if we have a functional of this form, instead of getting one Euler-Lagrange equation, we get many Euler-Lagrange equations, one for every direction, so there will be n of them. So let me say for j going from 1 up to n, the nth one is going to be the following: dg df sub j, evaluated at f, underbar here, f dot t, and these are f of t and f dot of t, minus ddt of dg dfj dot, evaluated also at f of t, f dot of t, and t. And this will equal 0 for each component. And that's key. So we just need to take the same derivatives, but now with respect to fj and f dot j. This will often be what we deal with when we're looking at classical mechanics problems, because classical mechanics takes place in more than one dimension. So what we're often looking at are trajectories, which are functions from R into Rn. Good. Okay, now we've done a lot of abstract formalism so far. I hope I've convinced you that a function satisfying these equations is stationary. But the only way to really get a grasp on what's going on is to jump over to do some examples. So let's do that right now. All right, The best way to get a handle on what's going on with calculus of variations is just to hop in and do some examples right off the bat. Recall that our whole goal is to define functionals from a space of functions to the real numbers, and then optimize or find the function that optimizes that functional, either by minimizing or maximizing it. So we'll look here to come up with some real cases in which that's what's going on. Let's hop over to OneNote so that we can get started. Okay, so let's first consider the following example. And that is to find the shortest curve between 2 points. Okay, so first of all, notice that the input is the curve, and the output is the distance. So I could write this in the following way. Let's say that the length of my curve, C, is the length of curve C. And let's fix the endpoints with endpoints A and B. And let's say that both of these vectors are in Rn. Now, we'll do this general case a little bit later in the video. But first of all, I want to focus on just R2. And that's for one simple reason, which is that I want to be able to draw what's going on. All right. Well, we know that we can use calculus of variations most easily if this object can be expressed as an integral. So let's ask ourselves this question. Can this be expressed as an integral? Let's go ahead and draw a curve in 2 dimensions. So here's our point A and here's our point B. Let's also say that if I put this in the xy plane, so this is the x direction and this is the y direction, let's suppose that this curve can be written as the graph of a bijective function. And in fact, do we need bijective? I think we might just need injective. An injective function let's call it f, going from A, B into R. Good. And actually, sorry, not A, B. We'll need to label the x coordinates of these points. So this will be A sub x and B sub x. Let me extend my x-axis here. Okay, so A sub x to B sub x into R. Great. With f of A sub x is equal to A sub y, and f of A sub y is equal to, of B sub x is equal to B sub y. Great. Now, we actually can come up with a way of writing this as a, what is going on here? Hang on. Okay, so can we express now L of C as an integral? Yes, we can. So L of C is going to be equal to, well, what we need to do is start adding up the length of all of these little segments. So let's draw a couple of those in here. Maybe I'll do this in blue. So we want to add the length of this segment and the length of this segment, the length of this segment, and so on and so forth. And let's imagine that the width of one of these segments in the x direction is always going to be delta x. Okay, well that means that the length of our segment can be gotten from the Pythagorean theorem. So if this is delta x, this is, let's call these points x sub n and x sub n plus 1. We'll run over this index n. Then this is f of x sub n, and this is f of x sub n plus 1. All right, so what is the length of this segment? Well, it's just given by the Pythagorean theorem. It's delta x squared plus fxn plus 1 minus fxn squared, quantity squared, square root. And then we'll need to add all of those up. So let's say this is going to be the limit as delta x goes to 0, because we'll want to take the width of these segments to 0, of the sum from n goes from 0 to, let's say, n minus 1 of each of these little lengths. All right. Now, I guess I should be a little careful here. Let's let x not equal a sub x and x n, capital N, equal b sub x. Great. Okay, anyway, let's proceed by pulling delta x out of this square root. And I'm forgetting my limit here. Limit as x, delta x goes to 0, and going from 0 to n minus 1. Now delta x of, let me blow this up a little bit, 1 plus the quantity fxn plus 1 minus fxn over delta x squared. Now, the key is to notice that this thing is a Riemann sum. That's going to go from a sum over these x, over the index n, to an integral over x. And the way that we'll make that happen is by replacing this, noticing that this is just the formula for the first derivative of x. This is going to be f prime of x in the limit. Okay, so where does this limit take us? It's equal to the integral from ax to bx of the square root of 1 plus f prime of x squared dx. Good. So now we have what is clearly a functional. And it's a functional of the correct form. So we have L of, now we'll replace our curve C by this function f, and it's equal to, well, some function in the middle here, let's say g of f prime and x, which is the form that we need if we're going to use the Euler-Lagrange equations. All right, so what happens in our case? We need to figure out what this function g of f prime and x is. It is our 1 plus f prime of x quantity squared. All right, so now let's go ahead and find our Euler-Lagrange equations, which will tell us what diffie q's the solution to the minimization problem satisfies. So in this case, we only have one equation. I probably should have just said equation. And that equation is actually relatively easy to find because notice that in our case, this does not depend on f of x. Great. Okay, so what does that give us? Recall that the Euler-Lagrange equations say that the partial derivative, or sorry, the derivative with respect to x of the partial of g with respect to its second coordinate, so we denote that usually by partial f prime, is equal to the partial of g with respect to its first coordinate, partial f. But in this case, because this thing is 0, we can actually state this in a different way. We can say that the partial of g with respect to f prime is equal to a constant. All right, let's give that constant a name. Let's let it be capital A. So what is the partial of g with respect to f prime? We can figure that out without too much difficulty. It's going to be 1/2 times 1 plus f prime of x quantity squared to the minus half, and then we need to use the chain rule on the inside. So that's going to give us 2 f prime of x in the numerator. Or, canceling the 2's, it gives us f prime of x over 1 plus f prime of x squared, and then all of that in a square root. And this is equal to a. So let's box this equation. This is what we're going to try to work with and keep going to try to solve it. Well, it looks like what I'm going to want to do is move this to the other side and then square both sides. So let's go ahead and do that. I'll get f prime of x squared is equal to a times 1 plus f prime of x squared. Now I'll get the f primes all on one side and have 1 minus a f prime of x squared. Oh, and oops, this should be a squared at this point, is equal to a squared. Or f prime of x is equal to a over square root 1 minus a squared. Great. But it doesn't particularly matter what a is. What this tells us is that f prime of x is constant. And there's precisely one function which is constant, has a constant first derivative, and which passes through the points ax, ay, and bx, by. So let me state that out. There is precisely one function with constant first derivative that passes through the points ax, ay, and bx, by, namely the line through those 2 points. So there we go. We've solved our Euler-Lagrange equations and therefore our optimization problem. The shortest line between these 2 points, A and B, or so I should say the shortest curve between these 2 points, A and B, is precisely the line segment joining them. Good. All right, we'll return to this shortest curve example a little bit later in arbitrary dimensions. Next, let's do another example in 2 dimensions. This is a very famous example. In fact, I'm more or less contractually obligated to show you how to do this one because it's one of the most important historical examples in the development of the field. It motivated a lot of work in the direction of figuring out the Euler-Lagrange equations. And that is the example of the brachistochrone. So this is the curve that allows an object to fall in the shortest amount of time. Let's make that a little bit more formal. Okay, so suppose that we have 2 points A and B, once again. Now, of course, if we allow an object to just fall straight down, that is the fastest that it can reach this height, but it won't reach the point B necessarily, unless B is directly underneath A. So the question becomes, what curve should we pick if we want to minimize the time? So not the length of the curve, but the time the object takes. And so the first important question is, can we state this as an integral problem like we did before? The answer, somewhat surprisingly, is yes. And it took a long time to figure this out. So we're going to go through it in some detail. Let's once again work in the x and y coordinate system. Now, instead of thinking of our curve C as being the graph of a function from x to y, let's think instead of our curve C as being the graph of a function from y to x. Okay, so imagine that C is the graph of a function from let me say in quotations y to x, and what I mean there is from ay, by to the reals. Okay, such that f of ay is equal to ax and f of py is equal to bx. Now, the reason that we're going to do this sort of reversed like this is because we're going to use conservation of energy to help us out here. Conservation of energy tells us exactly how fast the object needs to be moving at every point. So when I say fall here, I should be a little bit more specific. I should say from rest. Maybe that's implied in the fact that I'm letting it fall rather than throwing it down, but let's be as explicit as we can. From rest. And that means that I know when I let my object go at A, how much total energy it has. Okay, so let's write that down. Total energy of object, let's say it has mass little m, then its total energy is mgay. Great. Now, at any other point, it must have equal total energy. The energy will be, let's say, at any other point y, the energy will be, well, 1/2 mvy squared. So we're going to think of velocity as a function of y plus mgy. And we know that that has to be equal to this quantity here. Good. All right. So let's start again building up a Riemann sum. I think that that's oftentimes the way that we're going to want to go about these problems. So the object is going to travel along small intervals again, except now these are going to be intervals in the y direction. How can we figure out the amount of time that the object is going to take? Well, let's imagine that along each one of these intervals, it travels with uniform constant velocity motion. And we can even see the path that it takes. So let's blow that up a little bit. So along this here, let's let this be y n. So we're going to go down, which is a little odd, but that's all right. And y n plus 1 here. And let's also make one more simplification before we go forward, just to make our lives easier. We'll move our axis so that this is just 0. So we'll set our y origin. Here I'll say new origin, such that the particle's total energy initial is 0. So all of these y's will be negative. Great. Okay, now let's do one more thing, which is to flip our axes. So now I'm going to say that this is going to be the plus y direction. The effect of that is going to be that I want to flip this sign. So I'll say this is canceled out and I have minus mgy. Since these y's will be positive, but I know that my potential energy should be negative down there. Great. That's going to make our lives easier when we think about integrating or turning this Riemann sum into an integral. All right, so this distance is going to be delta y for all of these. So let me fill that in here. And that means that I can get the length of this segment. Just as before, very similarly to before, I should say, this is delta y squared plus yn plus 1 minus yn, that quantity squared, is the length. But how long does it take to traverse that length? So the time needed is going to be equal to the length over the speed. But the speed is going to be given to us by this equation here. Good. So we'll pick yn as the y to plug in here. Let's solve this equation first for Vy. So this equation, with all of our different simplifications, tells us that 0 is equal to, well, actually, let's move mgy over. Mgy is equal to 1/2 mvy squared. We can cancel the m's. And therefore, that Vy is equal to square root 2gy. Good. All right, so the time needed for interval yn to yn plus 1 is square root delta y squared plus yn plus 1 minus yn, quantity squared, the square root of that whole thing divided by the square root of 2gy. Excellent. And again, for y here, we're going to plug in yn. Good. Now let's use the exact same trick as before and pull out a delta y. So that's going to give us delta y times square root 1 plus yn plus 1 minus yn, quantity squared over delta y squared, and all of that over root 2gy. Great. Now we could follow very similar steps to what we did before to turn our Riemann sum into an integral. This, of course, is the summand if we want the total time over all the intervals. But I think it's relatively clear that the integral that we end up with is that the time, actually, I should have given this a name, probably. So, well, I guess let's just do it down here. So the time t for the interval, or sorry, for the entire curve, is a function now of f, or a functional of f, and it's equal to the integral from a y to b y of square root 1 plus f prime of y over root 2 gy dy. Good. Now, once again, our integrand can be written in the following way. So it's g of f, f prime, and y. And in this case, it's our 1 plus f prime of y, quantity squared, over root 2g y. Notice that once again, it doesn't depend on f, which is a huge benefit to us as we try to work with it. So again, we're going to set the derivative of g with respect, or I'll go through it in the steps. So here's our Euler-Lagrange equation. I'll say EL for short. And it's that d dy of dg df prime is equal to dg df. Good. This doesn't depend on f. So this is equal to 0. So once again, I can just set this thing equal to a constant. But first I'm going to have to get it. So what is dg df prime? Well, just as before, I can use the chain rule once. So I'll just do that quickly. F of y squared to the minus half times 2 f prime of y, which is then equal to f prime of y over root 2 gy times 1 plus f prime of y squared. Great. Okay, and this thing is equal to a constant. So where does this take us? It takes us to the equation. Here, let me give myself a little bit more room. F prime of y over root 2 gy 1 plus f prime of y squared is equal to, let's use the same constant, capital A. And the solution strategy is going to be very similar to what we did last time as well. We'll move things around and then try and get a solution for this. Okay, if I do that in a couple of steps, I'm going to get f prime of y squared is equal to a squared times, actually, let me just maybe pull all that stuff out, 2g a squared y times 1 plus f prime of y squared. Once again, let's solve for f prime of y. So we'll get f prime of y squared times 1 minus 2g a squared y is equal to 2g a squared y, which then I can solve. I'll get f prime of y is equal to root 2g times a times square root of y over
square root of 1 minus 2g a squared. Great. Okay, so now I have a diffie-q I could actually solve. Let's box it. Notice that in the last case, I was able to just say that this was equal to a constant. Whereas here, I am actually going to have to integrate it. So this is a differential equation. I can solve. And we'll solve it in the normal way that we would solve any separable first-order differential equation, which is just to integrate it. So I now need to integrate both sides. So I'll get f of y is equal to well, let me say just the antiderivative for now. So some constant plus the antiderivative. What can come out? Root 2ga. And then root y over root 1 minus 2ga squared y. Good. And dy. Now, how do I actually evaluate an integral like this one that we see here? This isn't solved by many of the substitutions that you will have learned in an integral calculus class. Instead, let's try a solution of a different form. Okay, I would like for what's in here to look like 1 minus 1/2 of 1 minus cosine of theta. So in other words, I need for just this bit to look like 1/2 1 minus cosine theta. So let's fix that in as a substitution. So I have 2ga squared y equals 1/2 1 minus cos theta. Or in other words, y is equal to 1/4, I should say 1 over 4ga squared 1 minus cos theta. It seems a little bit random, but why this trig substitution works will become clear in just a sec. All right. Now, the first thing is to just plug this in the integrand itself without worrying about the measure. We'll deal with the measure in just a second. So upstairs, we have 1 over, well, okay, let's deal with the constants first. The 1/4 turns into a 1/2 because it's inside of a square root. Then I get a 1 over root g and a 1 over a. Then I get square root 1 minus cos theta. Good. In the denominator, I kind of fudged things, or not fudged things, but I was going for a specific result. And I wanted that this denominator was exactly 1/2 minus 1/2 plus cos theta. In other words, cos theta. But inside of a square root. All right, now let's worry about the measure. So dy is going to be 1 over 4ga squared times sine theta d theta. Okay, so let's just write that in. We have 1 over 4ga squared times sine theta d theta. Good. All right, let's do our cancellations. We have a power of a here, cancel with the power of a here. We have a power of root g here, cancel with the power of root g here. Next, we have a bunch of floating powers of 2 hanging around, and a g and an a squared left. So let's let the dust settle and pull all those constants out. root 2 over 8GA squared. Good. Then inside we have a 1 minus cos theta in a square root over root cos theta times just ordinary sine theta d theta. Great. Now I need to use an important identity from integral calculus in order to make this, or I should say from trigonometry, to make this work. Okay. Just to check that this works, if I have theta is equal to 0, then that implies that I have 1 minus 1 over 2. That works. And on the other hand, if I have theta is equal to pi, then cosine is minus 1. So this would be root 2 over 2. If I check, is root 2 over 2 equal to the sine of pi over 2? No, it isn't. And that is because I screwed something up. Man, this video is going to be hard to edit. Oof. Oh. Now, to make sense of this formula, we're going to need to remember an important identity from vector calc, which is that the sine of theta over 2 is equal to the square root of 1 minus cos theta over 2. So we should do some replacing of this numerator with that. So let's circle this, or maybe circle it, and note that this is going to be root 2 sine theta over 2. Next, we need to use another half angle kind of formula, which is, maybe let me combine this over here, that the sine of 2 theta, let me say 2 alpha actually, is equal to 2 sine alpha cos alpha. And I can use that to take sine theta and expand it in terms of sine theta over 2 and cos theta over 2. So this is 2 times sine theta over 2 times cos theta over 2. Great. And then lastly, I messed up my denominator here. Oh my god. Okay. Go all the way back. Oh my god. This is taking forever. Now, how do we compute an integral like this? This isn't amenable to many of the integration techniques that you will have learned in an integral calculus class. In particular, the substitutions that you've learned probably don't work here. So we're going to do something a little mysterious, but it will turn out that trig identities will save us in the end. So this thing, I would like to make this object look like 1/2 times 1 minus cosine of theta. Now, if I can do that, note that this whole denominator, maybe I'll do that in a different color, will look like 1/2 minus 1/2 plus 1/2 cos theta. And sorry, not 1/2, 1 minus 1/2, which is equal to 1/2 plus 1/2 cos theta. Okay, so let's keep that in mind and figure out what substitution is going to work here. So this would tell me that y is equal to 1 over 4 GA squared times 1 minus cosine of theta. Let's work out dy while we're at it. The 1 over 4 GA squared just gets taken out because it's a constant, and then I get sine theta d theta. This minus sign cancels the minus sign from the derivative of cosine. Okay, now we have a lot of plugging in to do and cancellation of factors. So let's go ahead and get started with that. This is going to give us a constant plus the square root of 2GA, the antiderivative, and now we got to start plugging things in. Okay, so first of all, let's do the numerator. The numerator is going to be the square root of 4GA squared, but I'll write that as 1 over 4GA squared. But I'll write that as 1 over 2 root GA times the square root of 1 minus cosine theta. In the denominator, on the other hand, we have exactly what we just worked out. 1/2 times 1 plus cos theta. Good. Next up, let's take the dy and rewrite it. So we're going to get 1 over 4GA squared sine theta d theta. And I'm going to do one sort of seemingly mysterious thing here before we keep going and rewrite this to pull a factor of 2 inside of the square root here. Now there was a 2 outside, so this is going to become a square root 2. Great. Okay, let's get to our cancellations. We have a root 2g here and a root 2g there, an a here and an a there in the denominator. Next, we can pull out all of our constants and see what we have left. Oh, oops. Okay. So we have that constant that we haven't dealt with yet, plus, well, our 1 over 4GA squared can come right out. And then we have the following antiderivative. We have square root 1 minus cos theta over 2 over square root 1 plus cos theta over 2 times sine theta d theta. Now we'll need our trig identities, and here are the ones that we'll need in specific. First of all, there's a half angle identity that relates to each of these. Sine theta, each of the numerator and denominator, I should say. Sine theta over 2 is equal to exactly the numerator, 1 minus cos theta over 2. Cos theta over 2 is exactly equal to the denominator, 1 plus cos theta over 2 in the square root, and I should have said that for the other one too. Now lastly, there's another formula that tells me that the sine of 2 alpha for some angle alpha is equal to 2 sine alpha cos alpha. And I can use that plugging in 2 alpha is equal to theta in order to rewrite sine theta in terms of sine theta over 2 and cos theta over 2. All right, so let's reduce this and see where the dust settles. We'll get sine theta over 2 in the numerator, a cos theta over 2 in the denominator, then a 2 sine theta cos theta, and sine theta over 2, sorry, and cos theta over 2, d theta. Great. Let's do our cancellations. We get the cosine of theta canceling with this cosine of theta. And so overall, the following. Oh, and that should become a 2. Sine squared theta over 2 d theta. Great. Now this integral may be unfamiliar to you. Let me actually make it a little simpler. I'll make this a d theta over 2 by multiplying a 2 on the outside. And so now we're trying to find the integral, or the antiderivative, I should say, of sine, let's say, sine squared alpha d alpha. This is an integral that you can, or an antiderivative that you can easily look up. Let's pull open a Mathematica notebook just to do it really quickly. So if I want the integral of the sine of alpha squared d alpha, it's given by alpha over 2 minus a quarter sine 2 alpha. Or equivalently, alpha over 2 minus a half, sine alpha cos alpha. Great. So let's write that in. Constant plus 1 over GA squared times, well, alpha for us is just theta over 2. So this is theta over 4 minus 1/2 sine theta over 2. Or actually, let me do it in this other way. 1/4 sine theta. Excellent. Now, this was, again, my f of y. And I also know that I want that to be equal to the x-coordinate of my point. So in this case, although we have, in a certain sense, solved for f as a function of y, we would just get it by rewrite theta as theta of y. That expression actually is pretty gross. It doesn't really help us understand the solution. Although if we wanted to plot it, that's what I would do next. Instead, let's group our equations in a particular way. So let's go back to where we made our substitution. I guess I'll need to use a new color. So here's what I have for y. And here is what I have for x. Notice that both of them can be expressed in some way that relates to the trig functions. So I have x equals constant. So let me say these are from my starred equations. X is equal to a constant plus 1 over 4 GA squared theta minus sine theta. And y is equal to no constant in this case, but also 1 over 4ga squared 1 minus cosine theta. So this is a parametric representation of my curve. What that means is that I write both the x and the y coordinate as a function of some other single variable. And since I'm writing them both as a function of some single variable, as I vary that variable, what I'll get is a curve in the xy plane. Now, once again, you'll want to use something like a plotting software in order to see what this kind of curve looks like. So I'll pull out Mathematica. So the prefactors are not important, nor is this constant that we're adding to x. Let's just look at what happens when we look at theta minus sine theta in the x direction and 1 minus cos theta in the y direction. Okay, so the x coordinate was theta minus sine, minus cosine of theta, or sorry, no, it's minus sine theta. And in the y direction, we have 1 minus cosine of theta. And let me take theta from 0 to pi over 2. Let's see what happens there. Okay, so there we go. Remember that we're actually looking at this upside down because we set our y-axis so that down was the positive y direction. We can even take theta a little bit further and see what happens. This kind of curve is a curve called a cycloid. Okay. And it can be described in another interesting way. It is the path mapped out as a circle rolls along by a point on the outside of the circle. So that is the big result that we were pushing toward. The brachistochrone curve is a cycloid. Okay, that does it for example 2. Now for the last example of this video, let's go back to the problem from example 1, but we'll do it again using this parametric idea, and we'll do it in an arbitrary number of dimensions. So rather than have what we had in example 1, where we had a function from x to y, we'll need a function of one parameter to all of the other spatial parameters. So we could think of something like time to all of the other all of the spatial coordinates. So let's draw this in 3 coordinates just so that we get a sense of what's going on. So once again, we have a curve that goes from A to B, and we would like to find the curve with the shortest length. All right, so in this case, we'll need to use a little bit of magic from line integration. Okay, so L of C in this case, well, we know that if I want to express this as a line integral, I can say that this is the line integral over C of just dl by itself. This is the scalar dl. And from a course on vector calculus, you know how I can write this. I can find some, so find some r that takes a particular interval, let's say in time ti to tf, into Rn. And then I can write it in the following way. So I should say such that the image of R is C, And now I can rewrite it. So this is the integral from ti to tf of the norm of the vector r dot of t dt. Great. So let me give myself a little bit more space because we're not going to be able to work with it in this form exactly. I'll instead need to write out this norm as a sum inside of a square root. So this all implies that L of c in our case, again using these line integration tools, is the integral from ti to tf of the square root. So I'm just using the definition of the norm of a vector of r1 dot squared plus r2 dot squared plus dot 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 plus rn dot squared dt. And I've dropped my dependence of the r's on t, but they are still there. I'm just saving a little bit of space. All right, so in this case, my function g doesn't just depend on r, but sorry, it doesn't just depend on one component, it depends on a lot of components. So I'll have g of the vector r of position, the vector r dot of velocity, and possibly t. And rather than having one Euler-Lagrange equation, I'll have an Euler-Lagrange equation for every direction. Okay, so let me point out that in our case, this is just this square root with the sum inside. So what are our EL equations in this case? Well, there will be one for every component of the R vector, so every j. So I'll say the jth equation is the following. Well, I need to take dg drj and equate that to the partial derivative, I should say, sorry, the derivative with respect to t of the partial derivative of g with respect to rj dot. All right. Once again, this is 0 in our case. So we can say that this means that the partial of g with respect to rj dot is a constant. All right, so let's do that. The partial of g with respect to rj dot, well, remember that g is equal to the square root of the sum of all of these things. So we'll be able to pick out exactly one of them when we take the chain rule. Let's do it. We'll have 1/2 r1 dot squared plus dot 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 plus rn dot squared to the minus half times, now is where the chain rule will pick out exactly rj dot. Okay. So after I do a little bit of cancellation, I get rj dot over r1 dot squared plus dot 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 plus rn dot squared. And this is equal to a constant. Good. Now let's take j not equal to k and see what happens with their two Euler-Lagrange equations. So for rj, we have rj dot over r1 dot squared plus dot 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 plus rn dot squared is equal to some constant. Let's give these names. Let's let this be a sub j. This is a sub j. And rk dot over square root r1 dot squared plus dot 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 plus rn dot squared, square root of all of that, is equal to some other constant. Let's call that ak. What I want to do to both of these equations is put the thing that's the same between them on the other side. So I'll get that rj dot over aj is equal to r1 dot squared plus dot 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 plus Rn dot squared. But that itself is equal to Rk dot over Ak. All right. So this means that for all of these things, for every direction, this quantity is going to be the same. The derivative of Rj with respect to time divided by this constant. So what can I say? For all j, Rj dot over Aj is the same. And what does that mean? Well, that means that Rj dot over Rk dot is going to be equal to what? Just Aj over Ak. And that's a constant. So for every parametric direction, the amount that I change the curve in one direction is just directly proportional to the amount I change the curve in every other direction. The only curve which satisfies this is a line. But notice once again that I'm not solving for Rj directly. In fact, it would be very hard to do that because all of these equations end up coupled. Instead, I'm able to solve in a certain parametric sense and say that the dependence of Rj on time is related to the dependence of Rk on time for all j and k. So once again, I've proven that the shortest path between 2 points in Rn now is a line segment that joins the 2 points. All right. Now, these examples don't necessarily come from sort of standard physics problems, right? We're not solving for the trajectories of objects at this point. We're simply doing calculus of variations in its most general sense. We find a functional that is a function that takes in functions and spits out real numbers, and we want to minimize that functional with respect to a function. If our functional can be written as an integral, then we have the Euler-Lagrange equations that must be true of the solution if the solution is extremal, which it almost always will be, and which we'll always assume that it will be in this course. So I hope that you're able to work some examples with calculus of variations, and in the next video, we're going to jump in and start working with Euler-Lagrange equations for actual physical systems using Lagrangian mechanics. I hope to see you in that one.